Okay, good afternoon, everyone. And I see we have a full house today. Uh, we made a lot of friends over the past couple of years, which is very good. Tells a lot about your character. It's very good. Today we'll be listening to the defense of Mahmoud al-Zuka. I'm just going to give a very quick, I haven't prepared anything, but I'm going to very quick history story behind him. So he came back in 2013, and he was accepted at the university as a TA. So he didn't have any faculty to work with, and I remember very vividly, very well. He was looking for someone to work with, and one day we happened to meet, or we were working at we met at Dr. Shields' office, and I remember him saying very clearly, Dr. Shields was asking him, I guess, who do you want to work with? What do you want to do? He was like, I want to work with Dr. Ndao, and he didn't know me really, so but somehow he might have read something about me or something. He kept repeating, okay, I want to work with him. so we end up, so I end up, he ended up working in my lab that way. So I wasn't looking for him. I wasn't trying to recruit him or hire him. He wanted to work in my lab. So actually, it turns out to be hopefully good for him, but for me, it's been excellent. Okay. So I'm really, really happy to actually have him as a PhD student this past couple of years. Now, one thing about him is that whoever comes in my lab, I typically, I'm just going to write something. I hope it's fine. I give them a design, a drawing, something like this, that says, this is for all PhD. In order to finish a PhD in my lab, you must meet a requirement. And this is knowledge, okay? And this is years you spend in my lab, okay? So in general, for a PhD student, your knowledge grows exponentially. So it grows very fast. Okay? At the beginning, you start learning, and it keeps growing, and it keeps growing. As a faculty member, my knowledge doesn't grow very fast anymore. I've learned a lot during my PhD years. Now I'm learning very slowly, incrementally. So my knowledge looks something like this. Okay? That means at one point, within the topic itself, at one point I happen to know more than Mahmoud or my PhD student. So I teach them. I sort of help them a little bit, guide them, show them about where to read, papers to read, and so on. And at one point, you expect it to know more than I do, and then start teaching me. Now, unless this happens, you do not graduate from my lab. So this must happen. So now the thing is, this must happen for every PhD student. The difference between PhD student or master student is when this happens. Okay, when this intersection happens. So for Mahmoud, it's been quite early actually, and it's not really fun knowing that your PhD student is actually teaching you a lot about your topic. So it's been the case for a couple of years for him. So I'm actually very happy that he was able to actually early on, get to a point where he became very independent and knew what to do without much of my supervision. In fact, in some of the topic that he does, he knows it way, way, way better than I do. It's like so amazing. So I'm quite happy to have him as PhD student, and he's my first graduate. So this is a big event for him. It's a big event as well for me. So let's welcome. Thank you.
So thank you for coming and welcome to the presentation of my dissertation defense. I'm Mahmoud. I'm originally from Egypt, Alexandria. I get my bachelor's degree and master's degree from Alexandria University. And hopefully when I'm done with this PhD, I'll go back to be an assistant professor in Alexandria University. The topic of my PhD dissertation research is related to using near-field thermal radiation in applications such as solar cells and to invent thermal computers. So my talk will begin with a little introduction about near-field thermal radiation and why it's important for engineers. Then I will go to the research topic I have covered during my dissertation years. My dissertation has two main bulks, application and manipulation of near-field thermal radiation. The application part has the energy conversion and thermal computing. So what's near-field thermal radiation? To understand near-field thermal radiation, you need to understand what does thermal radiation mean. Thermal radiation is electromagnetic radiation emitted by all kinds of materials found around us at temperature above 0 Kelvin. You know that all materials are composed of charges, positive and negative charges, and they are vibrating due to the thermal energy they possess. So if you consider one charge vibrating inside the bulk, and see the radiation coming out of this charge. Some of the radiation can cross the interface between the bulk and the vacuum and can have propagating waves. Those propagating waves can travel for good, can travel for very long distances. And those waves are the ones who comprise the thermal radiation we know in our engineering applications. And the black body radiation is just calculating how much the maximum the vacuum can support these waves. So there is another kind of waves that can exist. Those waves are called evanescent waves. As you see here, the waves cannot propagate along through the vacuum. They are just decaying away from the surface exponentially, and they are from the total internal reflection. So what will happen if you bring another body closer to the emitting body, very close to the emitting body? Then you will have the propagating waves and evanescent waves participating in heat transfer, and you will have an increased rate of heat transfer. So it is all the waves that can happen in the material. There is a third kind of waves that cannot propagate in vacuum nor in the bulk. They are called surface waves, and they are emitted by charges near the interface. So here comes the distinction between the propagating waves and evanescent waves. Far field thermal radiation, or the thermal radiation used for engineering applications, which we know is comprised of the propagating waves. If you bring separation distance very close between the emitter and the receiver, you will have the evanescent wave from total internal reflection and surface waves take part in heat transfer. So why is very interesting? The near field thermal radiation is very interesting for engineers. You can understand or appreciate the importance of near field thermal radiation from this dispersion relation. Dispersion relation is just a relationship between the frequency in space and frequency in time. And if you notice, it's comprised of dots. Every dot represents a wave state or a wave solution. The more the dots you have at any frequency, the more the heat transfer you will get. So this green area is the propagating waves that can propagate in the vacuum and in the bulk. The blue region is those from total internal reflection. And the most interesting ones are the surface waves, which cannot neither propagate in vacuum or the bulk. You can notice here that those surface waves has some kind of spikes. You see these spikes mean that there are many states to transfer the energy around this frequency. This is the one responsible for the spectral selectivity of thermal radiation. So now we understand what's near field thermal radiation, why it's very attractive for engineers. It has three main characteristics. The first one, it has increased heat transfer than the far field thermal radiation. It gives you a chance to control the heat transfer. If you manipulate the separation distance, then you can control the heat transfer rate. The third one, and the most interesting one, that it can work as kind of laser. Like you can have the heat transfer by thermal radiation happen around a certain frequency. And that's very interesting for applications such as thermophotovoltaics, which are a very new kind of engines or very new kind of energy converters that convert heat to electricity without any moving parts. The problem of these modern engines that they have low power density and they have low efficiency. So if you have your heat happening around a certain frequency like this, then you can boost the efficiency of those engines. And also from the increased heat transfer, you can increase the output power density of those engines. Second interesting application is for photolithography. Photolithography is one step in microfabrication. It happens with light usually, but the problem that the minimum feature you have is limited by the diffraction limit of light. For near field thermal radiation, you can go beyond this diffraction limit of light. The third application, very interesting, is the heat-assisted magnetic recording that will enhance or increase the data storage intensity beyond what we have today. You know that most of hard drives are working by storing the data on a magnetic media. If you use heat with magnetization of the material, you can control very small area of this magnetization media to magnetize. So you can write your data on a very small area, as small as 50 nanometers. And one third application is for spectroscopy. When you heat the material, it have every single material have its own characteristic evanescent waves. If you are able to scatter those evanescent waves with an AFM probe and do spectroscopy for those waves, you can distinguish between many kinds of material. So that's the near field thermal radiation. I will go ahead and present my dissertation research, and I will begin with the application to energy conversion systems. So I will begin with near field solar thermophotovoltaics, which are used to convert the solar light to electricity, but not as usual solar cells, which have only a photovoltaic cell. So why we are interested in this kind of research? This chart shows the energy sources for the MEMS devices or the micro electromechanical systems. You can find here there are batteries, thermophotovoltaics, fuel cells, and so on. The problem with most of power sources used for micro electromechanical systems, they have finite lifetime. You need to recharge them, or the power density is not that high. So you need to have an energy source that has as long lifetime as you can, and you need to have it very compact. So to have a higher lifetime for this kind of devices, you may use a renewable source for your energy converter. But the problem with the renewable sources is that they have still low power density. So one way of solving those problems to use solar thermophotovoltaics. So why we use solar thermophotovoltaics, not just the solar photovoltaic, the usual one? It has a maximum theoretical efficiency of 85%, which is way higher than the single junction PV cell of 41%. And it has two sources of energy. It can be powered by sun or by heat. And energy storage is possible with this kind of devices. The problem that they have lower energy density. So if you introduce near field thermal radiation, you can expect to increase the energy density of those devices. So that's a model of a solar thermophotovoltaic. You have the solar energy here, and you need to convert it to electricity. Usually, the solar cells convert the sun to electricity through a p-n junction, a semiconductor. But introducing an absorber and emitter between the sun and the PV cell boosts the efficiency of those kind of generators. So this system is composed of a lens that concentrates the solar light and an absorber that had a photonic crystal structures, such as shown here, like it has the structures that are kind of holes, cylindrical holes. The interesting thing about these photonic crystals is that they has a high emissivity at shorter wavelength where the solar radiation happen. However, they have low emissivity where the losses happen to the atmosphere. So they maximize the absorption of the sun. We have a tungsten emitter which converts the absorbed solar radiation to near field thermal radiation absorbed by the indium gallium arsenide photovoltaic cell and create electron holes which comprise the photocurrent. And the rest of the energy absorbed not converted to electricity is just rejected out of the system through this microcooler. So that's a normal solar thermophotovoltaic. If you need to make a near field solar thermophotovoltaic, you need to decrease this separation distance to very small values. So this curve will make you appreciate why near field thermal radiation might be interesting for these kind of devices. That's the separation distance between the emitter and the PV cell, and that's the heat transfer coefficient between them. You notice that from the tungsten to the indium gallium arsenide PV cell at far field, that's the heat transfer coefficient is kind of low. Decreasing separation distance increase the heat transfer coefficient exponentially, and it can even exceed the black body radiation. So you should expect from these systems to have higher energy density than usual systems. And the other advantage of having the absorber emitter between the sun and the PV cell is enhancing the efficiency. How this works, That's the quantum efficiency of the indium gallium arsenide, the green curve. And the quantum efficiency is just the conversion efficiency at every frequency. Like at every frequency or at every photon energy, you have different efficiency. You can notice that there is a peak here around 1 electron volt. And this peak, you have the highest efficiency. You wish all your radiation happen at this peak. If you have a laser working at this peak, you will have the highest efficiency possible of these cells. So the solar radiation in blue here, that's the solar radiation, has a very wide spectrum, and it does not target the peak of the efficiency. If you just introduce the emitter between the sun and the PV cell, you are kind of tailoring your spectral heat transfer and make it to align with the peak of the efficiency of the solar cell. So you have both advantage of increasing the power density and increasing the efficiency. So how can we model this? We have three parts of the model. We model the absorber emitter, we model the near field thermal radiation, and we model the semiconductor. Here I'm going just to display the model of the semiconductor. In this model, we solve the minority carrier diffusion equation, which account for the electron hole generation from the absorbed radiation, and it accounts for the recombination rate. You know, once you generate an electron hole, the electrons go to the depletion layer and pass the other side to form the current. Unfortunately, not all of the electron holes generated participate in the current. Some of them recombine and annihilate each other, so they does not participate in the photocurrent. And the third term is the diffusion term. The boundary condition used here, that there is no excess carrier concentration at the depletion edges, and there is prescribed recombination rate at the contacts. So the first piece of result I'd like to share with you is the most interesting one, is the output power density out of these energy generators. I'm displaying here the separation distance on x-axis and the power density on y-axis. As you see here, at far field or at large separation distance, the energy density is kind of low, and the less the separation distance, the higher the output power density. The three colors are corresponding to three temperatures of the emitter, and the dotted line is the rejected heat, and the solid line is the output power density. To give you a sense of numbers, this is the power density out of a state-of-the-art solar cell. So the normal solar cell have this output power density. You can reach up to 30 times higher in power density than the normal solar cells. However, there is a problem that with increasing the output power density, you are increasing the rejected heat from the cell. So the rejected heat might be, to give you a sense of number, also this is the rejected heat for modern electronics. So the rejected heat here is not a problem as long as you have an emitter temperature less than 2500 K. Second piece of results I'd like to share is the solar concentration here on y-axis versus separation distance. Of course, the less separation distance, the higher energy required to keep the emitter at constant temperature, and the more solar concentration needed. So the limitation for solar concentration will be the concentration of a single Fresnel lens, which is 4,600. Below this, you can achieve that system. So it also imposes a limitation at high temperature of the emitter, like lower than 2,500 will not be a limitation for your system. The third piece of result is the absorber emitter efficiency, which is the ability of the emitter to transfer the instant solar power to the photovoltaic cell. The lower separation distance, the higher the absorber emitter efficiency, and this is one of the main findings of our research. By just decreasing separation distance, you can increase the absorbed energy by the system. And why this happens? You have the losses from the absorber emitter. They are just a function of temperature of the emitter. As long as the emitter temperature is constant, then the losses are the same. So once you are decreasing separation distance, you are increasing this term, and you are increasing the solar incident because you are increasing the concentration, while the losses are constant. So you should expect decreasing separation distance will increase absorber emitter efficiency. The last piece of result is the efficiency of the system. I have two efficiencies here. The thermophotovoltaic efficiency, which is the efficiency of the absorber emitter and the PV cell, and the efficiency of the total system. So the efficiency of the thermophotovoltaic is in dotted lines, and the efficiency of the total system in solid lines. You notice that total system has a low efficiency at far field when separation distance is higher. And why is this? Because near field thermal radiation has not taken part yet. Once near field thermal radiation take part, the efficiency jump high. So we can take out of our research that the lower the separation distance, the higher the absorber efficiency you will get, and the more output power density you will get. However, you have two drawbacks: the increased rejected heat and the increased solar concentration. The optimum range for efficiency-wise would be 800 nanometers. So if you would like to fabricate a system like this, you should target separation distances below 800 nanometer. And this is the highest efficiency possible. You notice that separation distance is a tiny separation distance, 10 nanometer, which is not practical. So that's one part of my dissertation research, that's targeting the energy converters. The second part of my research regarding applications is to invent thermal computers. And for this, to achieve a computer, you need to have a memory, you need to have the logic circuit. So the logic circuit has a building block, which is the thermal diodes or the thermal rectifiers, and we have achieved both in this research. So why you are interested in having thermal computers? We have two or three motivations for having thermal computers. The first one is the energy crisis. You have problem with energy now. Electricity is scarcer than before. And on the other hand, you have waste heat of 60% of the total energy used. So you have myriad of heat that you can use in other applications, such as computations. So imagine that you have a computer that can be powered with heat and can store data, and instead of charged or not charged, 1 or 0, it will be hot or cold. So those computers can be powered with this waste heat. Another incentive that you can design a computer that can work at really high temperature. If it works with heat, so you don't care for overheating. So you can have this computer to work in harsh environments, such as space exploration. You know that we have reached Mars, but the next step after Mars would be reaching Venus. Problem with Venus, the temperature, the ambient temperature in Venus is 600 C. And modern electronics we have today has a peak temperature of 200 C. So using electronics in Venus is not an option. Like, you need to invent some other technology to replace it. And yet, till today, we don't know much about the core of our Earth because of the high temperature. So if you have these thermal computers, you can invade those environments and know more about them. The third incentive, that if you are able to control heat the same way you are controlling electricity, then you can control the heat the same way you are controlling electricity. Like, you can have a switch, turn the heat on or turn heat off. Now, if you need to turn heat on or turn heat off, you need to use a fluid, usually. But fluid is not applicable in all applications. So if you are successful doing this, you can apply thermal storage in many applications, such as consumer products or space exploration. The first part of to realize thermal computers is to invent a thermal memory. So what thermal memory is composed of? It's a thermal system, has certain boundary condition, but this system can achieve one of two equilibrium states. You know that thermal system has only one solution once you have two boundary conditions. Here, I'm trying to have a system, thermal system has two stable states. So in literature, like, people try to introduce thermal memory using vanadium dioxide, which is a material that can convert between dielectric or metal around 340 kelvins. The problem with this, that it has a fixed operating temperature. You can achieve a memory only around this temperature. The second attempt was very abstract. It was just theoretical work to use like a chain of molecules, two chains of molecules connected with a central molecule with nonlinear force here. It's very abstract, and it's not applicable in the near future. So here we are trying. So here we are trying to invent a thermal memory that can be fabricated easily and can be directed to applications right away. So our system is simple. It has a terminal kept at high temperature, the lower terminal kept at low temperature, and we have the head here, which stores the information as hot or cold. So once you heat this head, it stays hot. Once you cool this head, it stays cold. The head is connected to the lower terminal via a support that can be thermally expanded. So this head is free to move up and down. So how can you achieve a thermal system with two stable states? You need to have nonlinear heat transfer to the head. So this is the head, and this is the heat input, the heat output. The heat input from the near field thermal radiation between the head and the hot terminal, and the output heat from the head would be the heat conduction through the support. If you need to have a thermal memory, if you need to have a system with two stable states, you need to have one of these heat components to have nonlinear interaction. So the conduction has linear profile with the head temperature. So we engineer the heat input to the head via near field thermal radiation and try to make it take this weird shape. So this shape has a region here where negative differential thermal resistance happen, which is counterintuitive phenomena. Like usually for heat transfer, the higher the temperature difference, the higher heat transfer you're expecting. However, at this region, the higher the temperature difference, the lower the heat transfer. How can you achieve this? By coupling the near field thermal radiation with the expansion in this microstructure. And this is very similar to a ball over a hill, this model. Here the ball has two stable states and has one critically stable state, which is the threshold between the two states. So here in this system, you have temperature for the higher stable state, another temperature for the lower stable state, and this is the threshold temperature. If you heat the head above this threshold temperature, you are expecting to have 1. If you cool it, you are expecting to have 0. We have solved this model, 1D model, for that system and keep the base at 600 Kelvin, and they give profiles for heat such as shown here. This is very similar to the cartoon I have shown in the previous slide. However, there is one drawback of this system, that the width of the stem, which is the support to the head, is very small. Why is this? Because the conduction is way stronger than radiation, so you need to limit the heat conduction to make it interact with thermal radiation. To solve this problem, we have introduced a 3D model for a practical design. To decrease the heat conduction from the head, we have this serpentine design. And in this design, we have solved the 3D model with thermal emission losses included and temperature-dependent material properties. We used COMSOL with MATLAB to solve this complicated model, and it gives similar results to what I have shown in previous slide. So next, I will introduce the dynamic of read-write cycle. So that's the thermal memory in action. First, it starts at room temperature, then writing 1 by heating the head a little bit. Once you heat the head, it should keep the 1 state, should be kept at high temperature. And writing 0, if you cool the head a little bit, it should snap back to the lower state. So the outcome of our research, that storing information in form of heat is possible. This kind of structure I have shown is can be fabricated easily. And why this kind of memories are very interesting? Because they are immune to high temperature, they are immune to intensive radiation, and they can be made of almost any kind of material, and they are not bounded by a certain temperature limit as the phase transition materials. The challenge here is to achieve more stable states and to control the nonlinearity in near-field thermal radiation more efficiently, and this will be introduced by the end of my presentation. So that's the first part, to realize thermal computers to achieve a thermal memory. The second part is to achieve thermal rectifiers, or kind of thermal diodes. So what are thermal diodes? They are devices that can allow heat to flow in a certain direction in higher rate than the reverse direction. So the proposals to achieve those in literature was to use asymmetric structures such as silicon nanowires. You see that's nanometric scale devices, or to use non-uniform mass loading for carbon nanotube or boron nanotube. And some researchers proposed to use near-field thermal radiation with phase transition material in between, and to move this material between the two terminals without mentioning how you can do this. So most of the proposals are using exotic materials or systems that cannot be fabricated with current technology. So in our research, we are proposing a very simple idea, is to have two terminals and a structure that can be expanded with heat. It's very similar to the structures used for the memory. And as you see here, the side that's connected to the structure, if it's kept at higher temperature, this gap will be smaller than the other case when you flip temperatures. So you're expecting this to have higher heat transfer than the other case. Although the proposal looks simple, looks easy, however, you have two main challenges. How to make good thermal insulation for the system, to make the radiation comparable to the conduction, and how can you make this separation gap sensitive to the temperature of one of the terminals. So we have fabricated this micro device. It's a proof of concept micro device for a thermal rectifier. The concept of the device is shown in this cartoon. The device has a fixed terminal, a moving terminal. The moving terminal is moved by a V-beam chevron. It's V-beam like this. If you heat the beam, it will expand and it will snap up like this and change the separation distance between the fixed and moving terminals. That's the case of the forward bias. When you heat the moving terminal, you can achieve a smaller separation distance than when you flip the temperatures. So in the isometric view here, the device is completely suspended in vacuum through those supports. Each support is just 10 micron thickness, and the device is symmetric about X and Y axes to increase the rigidity of the device and decrease the losses. The device has these main components. It's the blue shaded area is the fixed terminal. The red one is the moving terminal, and this is the bent beam, the actuator mechanism. And you have a spring here to give the moving terminal the freedom to move in plane. We have two heaters, platinum heaters, printed on the fixed and moving terminals to control both temperatures and measure the heat transfer. So the fabrication of this device has been undertaken inside a clean room, and this began with a silicon over insulator wafer. That's the silicon layer, device layer, 20 micron thickness of silicon that will comprise our final device. And the substrate is 380 microns. In between, there is an oxide which will work as an etch stop. The first step of microfabrication is to add a dielectric layer of silicon dioxide on top and bottom of the wafer to insulate the platinum heater, which will come next. And we have made this silicon dioxide through wet oxidation in furnace at 1100 C. We deposited further another layer of silicon dioxide by plasma-enhanced chemical vapor deposition, and this will work as an etching mask while we release the device. The third step is to fabricate our heater. We fabricate the heater with electron beam evaporation and followed by liftoff process. Because platinum is a noble metal, it's hard to stick to most of materials, so we have a tantalum adhesion layer of just 10 nanometer to promote the adhesion between the platinum and the silicon dioxide. Next step is to do front side etching, which will give you the actual shape of the device. And this was by reactive ion etching for the front silicon dioxide, and then deep reactive ion etching for the silicon device layer. The last step is to release the device to make it completely hanging in vacuum by etching the backside by reactive ion etching and deep reactive ion etching. So this is the device during the fabrication steps. Here I deposited the heater. Here I fabricate the front side of the device to realize the shape of the structures. And this shows the backside window via an IR camera. And this shows you how the backside etching is aligning perfectly up behind the device. Although the device is hanging just by 10 micron supports, you can notice that it's durable. How can I remove the pointer? Move the laser. So although this support is just 10 micron thick, it's durable. It can like I am pushing with my needle my device in plane, and you see the device is moving, and it does not break. So it's kind of durable structure. So to appreciate how much the separation distance change with heating and cooling, this my device, I'm applying heat on and off to the moving terminal to change the gap, and I'm just giving different shots in different places in the device. So this very tiny motion will be proven to manipulate the heat transfer between the fixed and moving terminals, as will be shown in the thermal rectification results. So to do measurement for this device, we need to have all the measurements to happen in vacuum. We have a stainless steel vacuum chamber here with a vacuum pump to evacuate the air. Inside the vacuum chamber, we have a chuck that's temperature controlled through this temperature controller. Our device lie on the chuck here, and we have two heaters on each terminal, and we supply each heater with a current source that supply the power and measure the temperature of every coil. And we connect everything to LabVIEW for data acquisition and control. So that's the thermal rectification measurement. So the measurement happen as follows. That's kind of a model for the system, a thermal model. We have heat supplied by the heater to the fixed terminal, heat supplied to the heater from the moving terminal. We have heat transfer between the two terminals and heat losses from each terminal. To measure the heat transfer, you need to calculate how much losses from either of the terminals. Here I choose to measure the losses from the fixed terminal. How can I measure the losses from the fixed terminal? I set the thermal temperature, the fixed one, to 530 kelvins, and sweep over the moving terminal temperature. So at certain point, at this point, the temperature of the fixed and moving terminals are equal. Based on the second law of thermodynamics, there is no heat transfer between the two terminals. That means that all the heat supplied to the fixed terminal will be converted to losses. The losses depend only on the temperature of the moving terminal. Therefore, for this curve, the losses will be the same. So when you calculate the losses with the energy balance, you can calculate how much heat transfer between the two terminals. The impressive thing here that these the losses from the cold terminal calculated at two fixed terminal temperatures, and they are co-aligning perfectly. So that's the thermal rectification results. The top two graphs are for thermal rectification, and the bottom two graphs are for heat transfer in forward and reverse bias. So the forward bias has an X marker, and the reverse bias has an O marker. These two graphs are for 3 micron separation gap. You see that the initial separation gap between the moving and fixed terminals. And we measure this at several temperatures for the lower temperature. You can see here that always the forward bias has higher heat transfer than the reverse bias. And we can achieve the rectification at temperature as high as 600 Kelvin. And this results for different separation gaps of 3, 4, and 5 microns. So what we take out of this research, that thermal rectification is possible practically, experimentally at high temperatures. We have achieved thermal rectification at 600 kelvins, and the maximum rectification was 10.9%. It's kind of not impressive, not very high, but we have chance for improvement. And the rectification is dependent on design parameters. So if we spend more time optimizing the design here, we can achieve higher thermal rectification. So that's my application section, the first section of the dissertation research. The last section will be manipulation, how to manipulate heat transfer by near-free thermal radiation to achieve more stable states in thermal memory and to achieve higher thermal rectification. So I'm proposing use meshed photonic crystals to achieve this purpose. In literature, the state-of-the-art research for enhancing near-field thermal radiation has two main interests, or two main approaches. The first approach is to use patterned 2D materials. 2D materials is just sheets of material. The thickness of this sheet is 1 atom. Usually they use graphene. And the second approach is use hyperbolic metamaterials that has weird structures like this trapezoidal tooth. The problem with those proposals that you are using exotic materials that we don't have yet any means to microfabricate those kind of graphene, and those structures are also complicated. And most of proposals are targeting nanometric distance from the emitter and the receiver. So we are trying to introduce something practical that can be achieved with current state-of-the-art microfabrication techniques. We are proposing use meshed photonic crystals. When they are meshed, the heat transfer is expected to be higher than when they are non-meshed. So from any engineer intuition, you can say that, okay, the heat transfer here will be multiplied by the surface area. That's true if you have the thermal radiation is a surface phenomena. This is true when you have the structure size is larger than the skin depth or the penetration depth of radiation. The penetration depth is kind of around 10 microns only. So if you have structures that are smaller than the penetration depth, smaller than 10 microns, then you cannot just deal with thermal radiation as a surface phenomena. You need to take into account the wave nature of radiation. You need to solve this problem truly and take into account the scattering between the two structures. So how can we consider the wave nature of thermal radiation? We need to go back to the initiation of thermal radiation, or to go back to the main physics of thermal radiation, which is the electromagnetic waves. So the electromagnetic waves, the scattering of the waves, propagation and generation, you need to solve Maxwell equations, which are Gauss law, Faraday and Ampere's law, with a simple modification by adding a fluctuating current to the Ampere's law. So as you see here, that's the emitter. If you need to calculate thermal radiation, you need to have a current source that's distributed around the emitter, and this current source should be fluctuating randomly. But there should be a relating this random fluctuation with the temperature of the emitter. This will be set by fluctuation dissipation theorem, which gives the correlation between the fluctuation in current, electrical conductivity, and temperature of the emitter. So That's how the radiation look like in real life. It's just emitting electromagnetic radiation that's vibrating at all directions in time, but these fluctuations are way slower than the actual fluctuations. The fluctuations are in megahertz. So we have made a model for this system. We have used Bloch theorem to simplify our problem. Since we have a periodicity in the x direction, we can only study one unit cell of the system. We have studied two flat surfaces, two surfaces that are not meshed, and meshed two surface. So to apply Bloch theorem, you need to have a Bloch periodic boundary condition on both sides. There are periodic boundary condition with the phase shift. The phase shift is determined by the Bloch wave vector. If you need to solve for all kind of states, you need to sweep the kx over all possible values which achieve unique solutions, which is from 0 to 2 pi. So in our simulation, we have applied a random current source with a white noise and a certain wave vector. We have achieved this energy flux, and this is very similar to the emissivity or the transmission factor between the two structures. If you integrate along all the possible values of kx, you get this energy flux. If you need to calculate the actual heat flux, you need to multiply this energy flux by the mean energy of Planck's oscillator. Then you will get the thermal radiation out of this system. So first of all, before proceeding to results, you need to understand how the wave propagates in this system. So to understand how the wave propagates in this system, you need to investigate the dispersion relation. Dispersion relation is relationship between the frequency in space and frequency in time. And every point here in this curve shows that there is a possible wave that can happen at this structure. I have made the simulation for structures with 3 micron tooth height, 8 micron tooth height, and 8 micron mesh tooth height. If you notice here, the more the dots you can find, the more heat transfer you are going to expect. So for 3 micron tooth height, if it's compared with the 8 micron tooth height, you can notice that there is double the states can be found. If you compare the non-meshed with the meshed photonic crystals, you can notice that there is a continuum of states here for the meshed one, rather than the pseudo gaps here. You find band gaps here at these frequencies, where you are expecting the heat transfer to have valleys here. So to visualize how thermal radiation works, you can see that the fields are they are similar to the propagation of fields inside a waveguide. So you have the first order mode, the second order mode, and the third order mode. And the modes are distinguished here. You can find that there is no nodes, there is one node, there is two nodes here. So to appreciate the effect of tooth height, we made the simulation for 3 cases for flat surface, 3 micron tooth height and 8 micron tooth height. We have calculated the transmission factor for different values of wave vector, of Bloch wave vector of 0.1, 0.25, and so on. And here at the last panel is the integrated transmission factor with respect to kx. So to give you a sense how these computations are exhaustive, one curve of those curves costs 600 hours of computation. Why? Because you are simulating a random process. You need to average the simulation along many runs to get rid of the white noise. So you can notice here the flat surface has the green curve. It almost has no peaks. It just has one peak here, one peak here. At the relevant frequencies, it not even exist at high values of wave vector. Introducing a short tooth will bring some peaks to the transmission factor, and the deeper the tooth, the more peaks you can introduce. And at very high values of wave vector and low frequencies. And the heat transfer calculation is by just multiplying this curve, this theta, with the integrated transmission factor. So the most important frequencies are the lower frequencies here. And to give a sense, how does it look like? These are the modes that are propagating at wave vector equals 0. They are standing waves here, and these are propagating waves in the x direction. To see the effect of meshing, we simulated those 4 cases with different meshing or different separation gaps, and that's the transmission factor at different kx values. You can notice that the fully meshed case has peaks that are higher than all other cases. And if you remember the continuum I have shown you in the dispersion relation is very obvious here at the integrated transmission factor. There is no values here for this meshed case. If you compare it to the other cases, they have values here at those frequencies. And those are the modes that can propagate in the material in those cases. So the main result out of this research is the total heat transfer with the change in the separation distance between the structures. We have done the simulation for TE waves. TE waves, that waves that electric field normal to the incidence plane, and TM waves, and both T and TM. So for most of the results I have shown and dispersion relation was for the TM waves. Unfortunately, the TE waves does not have any resonance. So the heat transfer is by propagating waves and total internal reflection. So it's very dependent on the surface area. That's why you can have the flat surface has higher heat transfer than the structured surface. And also, if you see here, the heat transfer of the 8 micron and 3 micron tooth height, they are almost the same here. If you turn on the TM wave, it's completely different. The heat transfer is higher than the flat surface because you have the resonant modes participate in the heat transfer. And you can notice that there is no much difference between the 2 cases of the tooths with different separation gaps. So those tooths are 0.5 micron separation and those of 0.8 micron, and there is no much difference between both. In total heat transfer, all of the structured surfaces has achieved higher heat transfer than the flat one. And this is the total heat transfer is scaled to the heat transfer between 2 flat surfaces at 7 micron separation gap. You can reach up to 90 times higher heat transfer than 2 flat surfaces separated by 7 microns. So out of this research, we can conclude that structured surface has higher heat transfer than flat surfaces. We can have achieved 26 times higher heat transfer than the separated surfaces. This can be applied to thermal memory and thermal rectification to enhance the rectification up to 2,500%. In the experimental measurement, it was just 10.9%. So that's the presentation of my research, of my dissertation research. That's the achievements of our dissertation research. We have published in 4 prestigious journals. This is still pending. And we have 1 patent out of these thermal memory and thermal rectification devices. So what you can get out of this dissertation or this presentation, that near field thermal radiation can achieve 30 times higher energy density than normal solar cells. You can increase the solar absorption by applying near field to this solar thermophotovoltaics. Thermal memory and thermal diodes are possible with near field thermal radiation. We have proven this experimentally. And structured surface can bring near field thermal radiation closer to practical applications. And my future goals or future work is to make resonators that work only with heat. So why resonators are important? They are used in all kinds of sensors, and they are the clocks of your CPU or your computer here. Now the oscillators are made of crystals that vibrate by electricity. If you are making them vibrate with heat, you can save a lot of power. That's first target. And second target, the oscillation with electricity need higher voltage. Generating heat, any kind of voltage can generate heat. So by coupling near field thermalization with this expansion, I'm expecting to have this interesting phenomena. Another interesting application to have two surfaces that are separated with nanometric separation gap, and the other surface is just flying in the air above the emitter. This surface is just flying in the air and held by the Casimir forces, which can be engineered to be repulsive forces. By the way, Casimir forces has the same origin of near-field thermal radiation. Both of them are from the fluctuating charges within the material. I'm going to investigate more complicated structures to achieve higher resonance, and ultimately, I wish I can build a thermal logic system that work only with heat. So I'd like to acknowledge the funding agencies which support our research and made all of this work possible. And the Egyptian government has supported partially uh, my stipend here. And I'd like to acknowledge my lab mates and my family here in Lincoln and my family in Egypt and my committee members. And any questions or comments are welcome. Thank you so much for listening.
So we'll entertain some questions. After you guys have asked, we'll first get questions from the audience without including the committee members. And then once you guys done asking your question, we'll ask you to leave, and then we'll spend some time with Mahmoud and ask him more questions ourselves with him. And then afterwards, we'll make a decision based on what we learned from him. Okay? If you guys, after you leave, you could, if someone you want to stick around to know the answer to his whether he passed or not, you feel free to wait around as well. We won't take extremely long time. Okay? You could feel free to ask any question now.
Like usually for solar cells, when you store energy, you store it in an external battery, and you use this electricity later on. So if you have this system, you can store the heat absorbed by the sun instead of storing in battery. So that's the mean. And also the excess sun that's absorbed can be stored in a thermal storage media. That's what I mean. When you store electricity, you convert the solar energy to electricity and you store it in certain battery. It has some losses in the way, and it's more compact to store heat than storing electricity. Thank you for the question. Any other questions? Yes. I am not sure. Like the problem of the speed, the thermal inertia. You are heating something. You need to wait till heat diffusion happen. However, if you make things smaller, you can have this thermal inertia lower. But that's targeting some applications that are very special. Like you don't have the technology to reach this high spot, so you can have a bulk computer that's not that fast, but it can withstand, can survive. So of course, like I have this question many times. Thank you for the question. So any other question?